This Afterpop is brought to you by the Nuclear Talent Scout. Looking for your next step in nuclear? Nuclear Talent Scout connects top talent with companies building our energy future. Register today at nucleartalentboost.com because your next opportunity could already be waiting. Hello, everyone, and welcome to the Afterpop, where we strip down nuclear ideas until they are as clear as mud. Well, hopefully clearer than that. Today, we're tackling a big question. What is reactor physics? Now, you might be thinking physics sounds hard, equations, symbols, maybe some late-night math homework, but reactor physics isn't just a stack of equations. It's about understanding how tiny particles, smaller than an atom, can create enough energy to light up entire cities. And don't worry, I'm not about to hand out a test. We're going to explain it like you're in science class, but maybe a fun one? So first, reactor physics. Our previous episode, we talked to Ikhwan Khaleb about his journey at University of Michigan studying reactor physics. So we wanted to create this Afterpop to dive in. So, what is reactor physics? Imagine you've got a giant pot of popcorn kernels. Each kernel can pop, but it needs a spark of heat to get things started. Now picture one popcorn exploding and bumping into its neighbors, making them pop too. That's kind of what's happening in reactor physics. Reactor physics is the study of how neutrons, tiny neutral particles inside the atom, move around, hit other atoms, and sometimes even cause them to split apart. That splitting apart is called fission. And when fission happens, it releases more neutrons, kind of like popcorn bumping into its neighbors, energy in the form of heat, the same way popcorn popping releases steam, and smaller atomic pieces called fission fragments. I don't really have an analogy for fission fragments. Maybe those are like the burnt, crispy pieces of the popcorn that you leave at the bottom of the bag. Now, reactor physics is about predicting and controlling all of that. It's the math and the science that answers how many neutrons will be released, where will they go, will they keep the chain reaction going, or will it fizzle out? If chemistry is about mixing ingredients to bake cookies, reactor physics is about making sure the oven doesn't burn them. Let's start with the neutron life story. We like to call this the neutron life cycle. Let's walk through it step by step, like a storybook. Step 1, birth. A neutron is born when uranium or plutonium splits. Step 2, fast childhood. At first, this neutron zips around at super high speeds, too fast to actually be useful. Step 3, slowing down. In most reactors, we want neutrons to calm down so they're easier to control. This happens in a moderator, often made of water. Step 4, adulthood, aka useful work. Once slowed down, the neutron might hit another uranium atom and split it. That's the chain reaction. And step 5, old age, aka absorption. Eventually, neutrons either escape, get absorbed by materials that don't split, or are captured by control rods. Understanding this life cycle is the heart of reactor physics. If too many neutrons escape or die off, the chain reaction stops. If too many are born and keep multiplying, the chain reaction could speed up dangerously. Reactor physics finds this balance. So let's talk about the balance. The balancing act is also known as criticality. Reactor physics uses the ideas of criticalities. Subcritical, meaning not enough neutrons. The reaction doesn't chain and the fire, quote-unquote, fizzles out. Critical, just the right number of neutrons. Steady, controlled power. This is kind of like the Goldilocks zone. Then there's supercritical. This is too many neutrons. This is where things can get out of control, overheated. Here's an easy way to picture it. Imagine a campfire. If you have just one spark, it might not light. If you add a few sticks, it grows. but dump a whole crispy Christmas tree on it, and you'll have chaos. Reactor physicists designed the campfire of neutrons so it stays in that Goldilocks zone. Not too small, not too wild, but just right. So let's look at some of the tools of the trade. What do reactor physicists actually do? Reactor physics courses at places like the University of Michigan, MIT, and NC State show that students learn neutron transport equations, fancy math that predicts how neutrons move. Think of it like weather forecasting, but for particles. 2. Diffusion models. A simpler version saying, on average, neutrons spread heat like from a campfire. 3. Criticality calculations. Using computer codes to see if a reactor design will sustain a chain reaction. 4. Reactor kinetics. Studying what happens when power changes quickly, like how fast you can press the gas pedal without stalling the car. 5. Fuel behavior. How uranium pellets inside rods can shape, heat, or even crack over years. 6. Control systems. How rods, coolants, and geometry keep everything balanced. It's a mix of math, computer modeling, and hands-on experiments, from working with reactor simulators to watching how neutrons behave in research reactors. So, why does it all matter? Reactor physics makes sure that reactors run safely, never too fast or unstable, helps design new types of reactors like small modular reactors or fusion prototypes, predicts how much fuel is needed and how long it will last, and guides how spent fuel is handled safely. Basically, without reactor physics, nuclear engineers would be guessing. And when you're dealing with atoms that can release millions of times more energy than a candle flame, guessing is not an option. In our episode with UMich alum, Ikhwan Khaleb, he used tea kettles and Jenga blocks in his TikToks to show analogies of what happens in reactor physics. Reactors are just the fancy tea kettles, making steam to spin turbines. And Jenga blocks are like chain reactions, carefully pulling and stacking blocks. One action sets off many others. Reactor physics teaches you the rules of the Jenga tower so it doesn't topple over. So, what is reactor physics? It's the science of keeping the chain reaction balanced, safe, and useful. It's popcorn that doesn't burn, a fire that doesn't fizzle, and a tea kettle that powers entire cities. And it's a career path, one that people like Ikhwan Khaleb are using not just to power homes, but to inspire the next generation in classrooms and across the world. Thanks again for listening to this episode of Naked Nuclear. We hoped you learned a little something about reactor physics. Thanks again to our episode sponsor, Nuclear Talent Scout. Until next time, stay curious.